Thank you. Yes, I'm talking about same issue we had just before, but it's a different method that we try to apply. It's the transient ion drift method, and we try to approach it by simulation. So what we try to do in our research is to extract material parameters by measuring our devices with a variety of measurements in all possible domains, so transient, AC, steady state, under illumination, in the dark. And then we want to fit these measurements using simulation, and we try to find a model and material parameters that explain our measurements. So this is what our former colleague Martin Neukomm did in his publication in 2019. And we had there the issue, like the same issue that was talked about before, that it's not that easy to distinguish between the different parameters that we have. And we especially observed a strong parameter correlation between ion concentration and ion mobility. So what you see here is an impedance simulation, once with varying concentration and once with varying mobility. And in short, you can't really distinguish anything here. It almost looks the same. We see a difference here in the plateau, but as soon as we go to the experiment and measurement, you won't see, for that cell at least, you won't see the plateau. You just see a rise to lower frequencies, and then you don't really get the information of the plateau. It looks even worse for IMPS. Here you really can't really distinguish anymore whether it's the concentration or the mobility that varies. And so also in the publication, we couldn't really determine concentration and mobility. We could just determine the product of the two. So we were very interested when we saw the publication by Moritz Futscher. Hi, by the way. Also in 2019, where he applied this method transient ion drift to perovskite solar cells. And it was later also applied by his colleague Lucy McGovern in 2020, again to another device. But the method was developed to measure copper defects in silicon. I think it was just silicon material, in 1993, where you have way lower ion densities, of course, because those are defects. You try to get them very low. But the method works like this. At short circuit, we have an accumulation of ions at the interface, so you don't see the gray of the electrode here, but there is like the electrode in here. And then you have this accumulation of ions. And this forms a sort of a conducting layer, which we will see as an increase in capacitance because the device gets kind of thinner viewed from a capacitance measurement standpoint. What we then do is we apply a bias to deplete the region from the ions, and then we apply short circuit again, and during that process of the reaccumulation, we measure the capacitance. Heiser then derived that nice formula here, which is an analytical formula for what should happen to the capacitance over time. And we should then here get our diffusion constant from that equation. And we have a second equation which gives us the ratio of the ion density, or a dependency of the ion density on the capacitance. Moritz applied this very successfully to devices. The results look very nice. Everything agrees. So we were interested in applying that. But of course, as always, if it looks too good, it can't be true. So there are some limitations that they seem to have applied in Moritz's case, but in general they don't apply. We assume that the accumulation is only drift driven, so we don't, diffusion doesn't play into the accumulation. The total ion concentration is conserved, and I think the first two are more or less reasonable for most devices. But then the space charge caused by the ions shouldn't affect the electric field, and this is usually something that is very difficult to achieve for perovskites, because ion densities usually affect the electric field. That's why we measure them. And the electric field is assumed to be linear, which is also quite hard to achieve. So the second two, or the last two, mean that we need a high doping density, which is significantly higher than the concentration of mobile ions. So we try to get over that by using simulation. And now, instead of simulating the AC pulse in transient, we apply a little trick. We just apply a voltage pulse in transient, and then we use a small signal analysis to do the impedance simulation on top of the transient results, and we get the transient impedance. We try to do that with ZHAW 5.2. The implicit Gummel solver that is implemented there, it's not that easy. It's very difficult to converge, and basically it wasn't suitable to use. We also tried an implicit Newton, which also didn't work very well. In the end, we came up with a semi-implicit Rosenbrock-Wanner algorithm, which gives us those nice transient currents, and it's reliable. It also has the advantage that it adapts the time step, so the large time is no problem for the simulation. And that's also the reason why this solver will be in the upcoming version of ZHAW 5.3 as the only transient solver. So going back to the device, where we have a lot of models included: series resistance, Langevin recombination, two ion species, traps, SRH recombination, and still we managed to run these simulations in 30 to 120 seconds on my laptop here. So they are also suited for optimization and trying things. You can just run them and look at the results. It's very nice. So when we go back to our initial problem, the parameter correlation, how does that look now with transient ion drift? Still on the devices that, with the parameters that Martin derived for in his publication, we now see that there is much less correlation. There is still some correlation, but we can clearly distinguish whether we vary concentration or mobility. And this is now an undoped device, so it's not dependent on doping. It's not dependent on assumptions that we had before. We can basically do that for any device that we can simulate, and we get nice uncorrelated parameters. Still, it would be interesting to know what's actually going on with this analytic solution. So we went a step back and tried single layer, high doping, only one ion species. We have a nice analytical solution, so it should be possible to get that result. We start with the second formula, where we actually, so this is the input from the simulation, what I put into the simulation, and this is then the ratio compared to the result at 1:15, because we only have here proportional to. We use this ratio, and we see here we have a very nice agreement, so that seems to work with this, with the two values in the beginning and in the end. We can fit the ion concentration, at least up to a constant. But then when we look at the transient signal actually that we get, it doesn't look that nice anymore. We somehow get this double exponential peak, and this is something we're still investigating, so I can't tell you why exactly this happens, but what we know is that we will probably have some influence of diffusion, And there is for sure a non-linear electric field. That's what we see in the simulation. And also the ion movement seems to affect the electric field. So the electric field still moves after the electrons and holes have moved into position. So it seems that the assumptions still don't apply. Also, here we have 4 orders of magnitude lower ion density than doping density. And it still seems to not work. But I'm eager to find out why this happens and why it works for some devices and what these devices need to fulfill. So to conclude, by combining the simulation with the new measurement method, we can overcome the limitations of the method, and we can also overcome the problems that we had with our initial set of measurements and simulations. We can thus better understand our devices and also better extract material parameters. And the next step will be to figure out how parameters or how the different parameters in our device actually affect our results. And in the end, it would be nice to measure actual devices, because we don't have the devices from 2019 anymore, so we can't measure them, and we'll need a new set of devices to measure. Thank you for your attention.